Very good.
Yes, it's okay.
Okay, good. Then we can continue. Next speaker is Renzo Caballero from King Abdullah University of Science and Technology, and he's going to talk about utilizing a malfunctioning 3D printer by modeling its dynamics with machine learning. So, the stage is yours.
Fantastic, thank you a lot. This work was equally contributed by my friend and colleague, Piotr Piekos. And yes, I'm Renzo Caballero from King Abdullah University, as you mentioned. Yeah. So I will for the motivation of this work, the background, some previous work, and finally I'll present the results provided for ICRA. So motivation. First, I start with some definitions. We say that a system or a robot can self-assemble when it can assemble and disassemble its own parts. It can self-replicate when it can fabricate copies of all its parts. It can self-repair, which is the one we care the most here, when you can fabricate copies of its broken parts or can repair them. We focus mostly on kinematic self-repairing, so actual physical machines. So what are the motivations for such robots? Here we see the picture of the empty park in Saudi Arabia and the Bangladesh in South America, where there are places where humans can only survive for a few hours or days without the correct equipment. So we believe that the society of autonomous robots is in some sense a solution to transform or colonize such places. We can think a bit more forward. Here you can see the surface of the moon and part surface of Mars, which are places where humans cannot survive for more than a few seconds without the work equipment. Also very expensive to send things up there. So we believe that a society of autonomous robots that again can self-repair, self-replicate is a good option, or maybe the only option to transform such places. Also, it can be our way as humans to extend our influence in the rest of the universe, which places where actually our lives are not ready for. And yet now with more scientific background. Von Neumann, he was the first scientist to formalize a theory for self-replicating robots in 1948. And he introduced a very important question. How can reliable systems be constructed from unreliable components? Because when a system has a broken part, that can be seen in some sense as an unreliable component. After Richard Feynman, he mentioned a similar problem in his famous talk in the printed room at the bottom. He mentioned, he gave a mental experiment where a machine fabricates a copy of itself at a smaller scale, and at the same time this second machine fabricates an even smaller copy at an even smaller scale. So he mentioned that in order to keep this process going as far as you want, you need the resolution of the fabrication to increase at some point. So at some point the resolution of fabrication will not be enough, so it will be unreliable, so you have to improve the resolution of the machines to keep the process going. So our test subject is a 3D printer. Why we choose a 3D printer? For many reasons. First, it's a robot that by default can fabricate parts, which is very convenient for self-repairing. And also, we always believe that in a society of robots, the 3D printer will in some sense the core, because we can fabricate parts for the other robots. And for the ones of you who doesn't know, a 3D printer basically can print three-dimensional bodies, as we can see here. From a 3D design, printing layers can end up printing a three-dimensional body. So in our previous work, what we do is we damage the 3D printer and we see if it can achieve self-repair. So what we do is to damage the tiny pulley here, is the pulley that controls the x-axis movement of the nozzle when the x-axis motor rotates. We substitute the ideal pulley, which is a circular one, by a triangular one, just to simulate a fault. And we attempt to print an ideal circular one and claim that we achieve self-repair. So when we do this experiment, what we do, when we are trying to print a circular one, what we got is a kind of oval-shaped one, which is not ideal. So basically we didn't achieve self-repair, but we ask our question, we ask the following question. In some sense, is this new pulley better than this one? What happens if we substitute the broken triangular one by this one and we attempt to print again? And when we do that, actually, we achieve self-repair in a second iteration, which was interesting. So we ask ourselves, it depends on initial condition when this works. So what we did is to create our own simulation of the printing process, and we tried many initial conditions, a triangular one, a small circular one. We also tried with this particular pulley, and we observed that all of them converge to the ideal one after few iterations. We tried with hundreds of thousands of initial conditions, all of them achieved self-repair. Still, we were not happy because, mathematically speaking, there might exist an initial condition that doesn't converge, but we proved on this paper here that actually, for any initial condition, this particular self-repair iteration always achieves. This iteration always achieves self-repair. And now, with this context, I will explain the paper I'm presenting today. So basically, what we did is we wanted to use neural networks in some sense to improve this self-repair capability. We don't want to add more hardware to the printer, we don't want to add cameras, we don't want to make the system more complex, because a more complex system is more difficult to repair. So we want to use the actual software of the 3D printer and try to train a neural network that works inside this actual hardware of the 3D printer to see we can improve the self-repair process. So what we do is to train a neural network with, with the simulator that we built here with our virtual 3D printer. We simulate many possible faults on the printer, and we utilize an open source data set with many 3D bodies, and we simulate basically many non-ideal prints. And from that non-ideal print, since we can compare the ideal one to the non-ideal one, we train a neural network to learn from a test trajectory. So essentially, the printer, before working, will attempt to print a test trajectory, and the neural network learns how to learn as much as possible from that test trajectory, and in that way, modify the reference that we want to print in order for the broken printer to print the ideal one. That is what we did on this work. So our data set is an open source data set from ThinkK. Here we can see, for example, a simulated ideal print and a damaged one. So this is a non-ideal one, this is an ideal one. So we use live GPT and independent live GPT. Here we can see some results. This is the ideal print, this is the damaged print. This is the corrected one. The error here is the average root square error in millimeters. What we do is we model the printing trajectories as a sequence of points, and we try to minimize point-wise the differences between the ideal one and whatever we want to print. We minimize that as much as possible. Neural networks try to minimize that. Here are the results. Here we can see the error for many different 3D bodies. It will be so interesting to see what happened here, but that will be future work probably, and to see how we can improve the performance of our system. Conclusion, we showed that we can use AI to help the 3D printer without making the hardware more complex. We showed that we can help improve the 3D printing process. We showed that AI can dramatically help to improve the self-repair. A special thanks to all these institutions that support this work. So just in 1 second, I'm from I'm a former student from KAUST, Hinata University of Science and Technologies, a very beautiful place to do research. Also a former student from the RIS lab. We're working on self-assembly robotics, optimal path planning, 3D printing, underwater robotics, and this is a picture of my former group. And thank you very much.
Thank you very much. We can take some questions. Please.
Do you know priori about the further shape of this gear? Or you used online during detect failure during work of 3D printer?
Sorry, do you mean the bit is aware of the shape?
Yes.
Okay. It's very funny. The iteration is completely open loop. At least there's no feedback of the shape. So the iteration process is independent of the initial condition, or independent of the initial time input. What I'm saying is the printer also have information about what is broken. It's the human who, in some sense, knows if something is not good, it's not going well with the time input, and we want to print a new one. And when we do that, in this case 3 times, we achieve the ideal one.
Thank you. Very interesting article.
Oh, thank you.
We can take one more question. I have a question. How about the generalization? So it learns these shapes, let's say, but in case like you end up with a totally different shape, which is maybe provided in the wrong way by human. So how can you?
Okay, so can you repeat the beginning of
The shape maybe it's not. It's partially known, let's say.
the question? Oh, I see what you mean. Sorry, I want to answer it 2 ways. First, this first paper, that was presented in ACC 2022, was this paper is completely open loop. If we know some information about the initial shape, then we can achieve faster conversions.
Sure.
That is clear. We didn't go in that direction. And also for it, again, on this, of the machine learning approach, we try to assume as few knowledge as possible, because we want to as guessing as possible. Actually, my colleague who was very interested, my colleague who participated more on the machine learning part, he was very actively asking me how to model the damage in the printer. I would tell him, no, we have to. But yeah.
Thank you very much. Let's take the speaker one more time.